Chapter 11 explores thunderstorms. We don't get too many thunderstorms in this part of the world. In fact, as you will explore in this chapter, the west coast of the United States, here in the San Joaquin Valley specifically, we experience fewer than 5 days a year on average when there is even a thunderstorm. And of course, we don't get them often, but it seems like when we do, they happen mostly in the springtime here in the valley, and they get them with more frequency in the nearby Sierra in the summer. We're going to explore how thunderstorms develop. We're going to explore how thunderstorms can cause flooding. We'll look at the world distribution of thunderstorms and also explore the reasons behind the causes of lightning and thunder. Here's a dramatic picture of a supercell thunderstorm near York, Nebraska. What is a supercell thunderstorm? Well, you're going to find out all about that in this chapter. Basically, the definition of a thunderstorm is kind of a no-duh. It's a storm that contains lightning and thunder. We all know that. These are convective storms that form because of rising air from the surface. There's some mechanism that causes unequal heating at the surface, like maybe the effect of terrain, a nearby mountain range, or some places heat up more or less than other places. Or you have shallow boundaries along the surface of converging winds, maybe a warm, moist wind from the south that's converging with a cold, dry blob of air coming in from the west. Or especially if you have rapidly diverging upper-level winds, which are coupled with converging surface winds, and the air rapidly rises, and if there's a lot of moisture on that air, you get those big, towering, convective-looking clouds that look like the head of a head of cauliflower in the grocery store in the produce section. If you get warm air that rises along a frontal zone, that can also be a trigger for thunderstorm development. Now, here on the West Coast, as I mentioned, especially here in California, except for the mountainous areas, thunderstorms are not a frequent occurrence. You can even get thunderstorms developing if surface temperatures are as low as 50 degrees Fahrenheit. That's only 10 degrees Celsius. That's not a particularly warm day, but if we do have a thunderstorm here on the valley floor in December and January, when temperatures sometimes only get up as high as 50 degrees Fahrenheit, it will be a maritime polar air mass coming down along the west coast from the Gulf of Alaska that will produce a destabilizing atmospheric condition and will cause this kind of weather, as the graphic shows you on the right. We're going to take a look at the different kinds of thunderstorms: ordinary cell or air mass thunderstorms, multi-cell thunderstorms, squall-line thunderstorms, mesoscale convective complexes, and supercell thunderstorms, and also the role of dry lines. It's a special kind of weather front. The role of dry lines in producing supercell or severe thunderstorms. As you can tell, as we're going through this list, it's increasing order of intensity. What you see on the right in that picture is an ordinary thunderstorm from a distance in its mature stage. They tend to flatten out on the top. An ordinary cell or air mass thunderstorm usually form in what we call a low shear environment. What this means is that the wind speed and or the wind direction don't change very much as you start from the surface and go up above your head. In other words, the wind speeds increase only a little bit and the wind direction doesn't change too much. These kinds of thunderstorms in this kind of an environment where you simply have a warm, moist air mass that rises into a cooler, unstable environment, maybe they pop up and they go away, and they pop up and they go away, and the whole drama takes place in less than an hour. These form when air is lifted by any number of mechanisms: convergence of opposing air masses, sea breeze fronts, that happens in Florida a lot, topographic irregularities, i.e. mountains, or cold air outflow from collapsing thunderstorms. That can actually produce additional thunderstorms. Over the years and decades, scientists have done research on thunderstorms and have come up with this three-stage model of thunderstorm development. First, you have the cumulus stage, where successive cumulus clouds grow taller and taller in the sky, and then the tops of those clouds go well above the freezing level. Initially, you have these friendly little cumulus clouds that aren't doing very much, and then they tend to get taller and more billowy and perhaps a little bit darker. In the cumulus stage, you almost exclusively have what we call updrafts, or warm air currents going up, as the red arrows indicate. Then when you start getting some downdrafts in that cumulus cloud, at the same time that you have updrafts, then you're in the mature stage, where often the heaviest precipitation occurs with the thunderstorm as the cloud top goes well above the freezing level on the atmosphere and levels off when it gets close to the top of the tropopause in kind of an anvil shape. Oftentimes, you will experience what's called a gust front. If you are ahead of the thunderstorm and you see the lightning and then you hear the thunder, but not a breath of wind is blowing, and all of a sudden you feel that cold gust of wind hitting you in the face, and then it starts to rain. That's the gust front, and that's because of downdrafts rapidly slamming down to the surface of the ground from the upper parts of the thunderstorm. Once the thing starts to weaken, then we get into what we call the dissipating stage of the thunderstorm, where you only have downdrafts, and that pretty much makes the cloud fizzle out. Only high, thin, icy cirrus clouds remain in the upper atmosphere from the dissipating thunderstorm. And this whole thing, with a typical air mass or ordinary cell thunderstorm, may play out in the course of an hour. It pops up, it goes away, the drama is gone. Now, more serious and more intense are multi-cell thunderstorms, which are lines of thunderstorms which can contain a number of thunder cells, each in a different stage of development. These often develop in regions of moderate to strong vertical wind speed shear, meaning that the wind speed rapidly increases as you go up in the atmosphere. Increasing wind speeds as you go up in the atmosphere can tilt the updraft, which rides up and over the downdraft, and that also enables the thunder cell to suck more warm, moist air up from the surface when you have the updraft tilted somewhat as opposed to going straight up. This produces an environment for the development of new storms as you get more downdrafts and gust fronts, which can then lift warm, moist air up from the surface and produce additional thunder cells. This is a great looking picture of a multi-cell thunderstorm complex. The middle cell is in the mature stage, the right-hand cell is in the cumulus stage, and then the left-hand cell is in the about ready to reach the mature stage. Sometimes these thunderstorms can be so powerful that they continue to build well above that flat anvil top. And this is what's called an overshooting top if it goes into the lower stratosphere. And this is kind of what this picture shows. There's a thing called the gust front, which is part of the very cold air that descends rapidly down toward the ground from a thunderstorm, cold, heavy air that slams on the surface that can act as a wedge to continually lift out in front of the thunderstorm additional warm, moist air, which can cause additional thunderstorm development. These gust fronts can be wind speeds of, say, 10 to 30 miles an hour if it's just a normal thunderstorm. But if the winds behind the gust front get particularly strong enough to cause property damage, meaning winds exceeding 60 miles an hour, then they're called straight line winds. As the warm, moist air rises along the forward edge of the gust front, you might get a strange-looking cloud called a shelf cloud, which is an indication of warm, moist air being lifted by cold, dry air on the surface. And sometimes you get a horizontally rolling cloud, which is in fact called the roll cloud, right near the gust front. It's a strange, eerie-looking cloud that appears to be sort of spinning on about a horizontal invisible axis just above your head. We can look at radar imagery in different parts of the United States, and sometimes we can see the leading edge of a whole bunch of gust fronts that merge together. This is called an outflow boundary. As cool, heavy, dense air from inside a strong or severe thunderstorm spreads outward, away from the storm's core, and the core of this series of storms is noted by the oranges and reds, that's where the heavy precipitation is going on, then that tends to lift out in front of it more warm, moist air, and along that outflow boundary, you can get additional thunderstorms because the outflow boundary then acts as a lifting mechanism to lift warm, moist air up from the surface. Here are a couple of dramatic pictures for you. Figure 11.8 from your book, there's a dramatic example of a shelf cloud associated with an intense thunderstorm, and figure 11.9 is a roll cloud, which is forming right behind a gust front. We can sometimes get from these strong downdrafts of cold air something called a microburst, which is an intense downdraft from a thunderstorm, and that downdraft spreads out horizontally once it slams down on the ground, and that tends to kick up dust, and that's kind of a visible manifestation of this cold, heavy air rapidly descending down to the surface, because once the precipitation falls from the cloud, especially if that precipitation evaporates, then that can really enhance the downdraft, and then you get this thing called a microburst. If the winds extend outward no farther than about 2.5 miles from the thunderstorm, it's called a microburst. If they extend more than 2.5 miles away from the main thunderstorm, it's called a downburst. The leading edge of this downburst or microburst can also evolve into a gust front, which can produce winds as strong as 150 miles an hour. This is obviously a great danger for aircraft, either departing an airport or arriving at an airport. So as I kind of go through this stepped art a little bit, well, it didn't quite work out. But if you play this PowerPoint, actually play the PowerPoint, you'll be able to see the stepped art and see the progress of how that microburst or downburst works. Then there is something called a squall line thunderstorm, which is an active line of thunderstorms that often produce strong gusty winds. And this is a radar image, a composite radar image, many of the Weather Service radars put together in the mid-Mississippi Valley, of a squall line. Here's Illinois, here's Indiana. You can see Kentucky over here, Missouri over here, and there's Tennessee, and then there's Arkansas. So you can see that this squall line of thunderstorms actually stretches all the way from lower Michigan right down to northeastern Arkansas. These can form an association with a cold front or even several dozen miles out in front of a cold front. These prefrontal squall lines often represent some of the largest and most severe types of squall lines that we observe in continental North America. Lifting by the advancing cold front can cause gravity waves in advance of the front, which causes additional lift. Rising air along the boundary of the cold front and along the gust front, coupled with the fact that the updrafts are tilted, really promotes the development of new cells, maybe stronger cells too. So this whole thing with these squall lines could actually go on for hours. To the rear of the storm, a downdraft can also form as precipitation from the cloud evaporates and then chills the surrounding air. Remember, evaporation is a cooling process, so that can even make the downdraft stronger. We call that a rear inflow jet. And if that rear inflow jet causes strong upper level winds to reach the surface, you can get those damaging straight line winds that occur on the surface in excess of 60 miles an hour that can cause property damage that I mentioned before. Here's an illustration, figure 11.14, showing how prefrontal squall lines can form as the upper airflow develops waves downwind, maybe as far away as 100 miles from the main cold front. This is a schematic of air motions and precipitation associated with a squall line that has a trailing stratiform cloud layer. Why is the trailing stratiform cloud layer important? Because you get lighter rain behind it, which tends to evaporate before it reaches the ground, and that can enhance that rear inflow jet, which can slam down on the surface and really enhance that gust front out on the eastern side of the storm, assuming that the storm is moving from west to east. Here's a more close schematic of straight line winds. Additionally, if the winds extend for long distances and cause lots of reports of property damage, they can be called derechos. And figure 11.19 is a photograph of a derecho line of storms moving through Texas. I wouldn't want to be in that mini-mart at that point in time, would you? We get, when we look at radar imagery, these images where you can see thunderstorms sort of bowing out from the main line. We call these bow echoes in association with these strong lines of thunderstorms called squall lines. These bow echoes are caused by very strong winds, the rear inflow jet, which slams down on the surface and bows the thunderstorm outward from the main line. You can see where a derecho is noted in each of these images. Sometimes this thing will sort of wrap around itself in kind of a mesoscale low pressure system and be called a mesoscale convective vortex. This one has moved from Missouri to Kentucky, as you can see here. You get also sometimes something called the mesoscale convective complex, as I just mentioned. These are individual multi-cell thunderstorms that can merge together. This is especially true in the eastern two-thirds of the United States, and especially in summer and especially at night. These clusters of thunderstorms can be 1,000 times larger than any individual thunderstorm. And while they can be destructive, they also provide very badly needed water for agriculture in the corn and wheat belts of the central United States. Mesoscale convective complexes can look very eerie on color-enhanced satellite images, and you can see how this one covers portions of 4 or 5 states. They can often produce hail, high winds, flooding, and tornadoes. Mesoscale convective complexes. We'll explore more about thunderstorms in the PowerPoint for Chapter 11, Part B.